Hello class, today we're going to explain the concept of hybridization and its relationship to geometrical structure. We'll also be able to assign hybridization to the valence orbitals of an atom in a molecule, knowing the number and geometrical arrangement of the atoms to which it is bonded. This goes well with Quest bonding orbital theories. Okay, so far we have talked about single bonds, double bonds, triple bonds, but there's a certain notation that goes with each of those. Whenever two orbitals overlap and form a bond, the first time it does this is referred to as a sigma bond. Sigma bonds can form between all types of orbitals. Typically, that's when you have two s orbitals overlapping. So when we think about s orbitals, I remember that it's a sigma bond because they start with the same letter. Sigma bonds directly refer to single bonds. When you have double and triple bonds, the first bond that forms is always a sigma bond. The pi bonds are the additional parts of that bond that forms. P orbitals, they're referred to as your pi bonds, overlap in a different way from the sigma bonds or the s orbitals, and they tend to overlap sideways or parallel to the bond axis. So whereas in the center here, this would be our sigma bond overlapping two s orbitals, the pi orbitals are the dumbbell shapes, and they overlap in this fashion as we see here. Whenever there's a pi bond that exists between two atoms, a sigma bond also exists. So as I was saying before, that first bond that forms is your sigma bond. The second bond in a double bond, or the second and third bonds in a triple bond, would be referred to as your pi bonds. Now the nice thing with pi orbitals, because they have multiple orientations, we are able to form triple bonds because there's also an orientation that goes out this way into that third plane of the axis. So we will look at triple bonds momentarily, and we'll see that again. But we first want to look at why these bonds form the way they do, and why do they hybridize. So my question is, how does carbon form four bonds? Well, we know carbon forms four bonds because the s and the p orbitals merge to form orbitals that are identical. If we were to look at just the geometry of carbon as it is, or not the geometry, the configuration of carbon, we know that carbon has four valence electrons, and we know the first two are paired, and then they would spread out like this. Well, if we were to look at it like this, there are only three spots available for carbon to form bonds, and they're all in the p orbital. So in order for it to form bonds, these bonds need to hybridize, which means the atomic orbitals we do have mix and form identical hybrid orbitals. The nice thing is that by doing that, we make all of the orbitals obtain the same energy. They hybridize so that they're at the same energy level. Whereas with the s and the p orbitals, we know that they are two distinct energies, and therefore it's a little harder for them to bond. So what happens is, when they hybridize, we end up mixing our s and our 3p orbitals to form four identical sp3 hybrid orbitals. If we take those four valence electrons, they now can spread out, and they have four open spaces that are of the same energy that can equally bond with other atoms. It's much easier for the overlap to occur when they are on the same energy level. Okay, so some of the examples we have here. We have sp3 hybridization with methane. That was what we saw on the previous page because they are all on the same level. We also have the same hybridization with ethane, C2H6. We have an overlap of one of the sp3 orbitals, and that is referring to this overlap here. And these other ones are available to bond with each of the three hydrogens that pop up here. Okay. So then that leads us to talk about double bonds. This actually helps us make a lot of sense of double bonds and triple bonds and why they form. It also explains why we can't form quadruple bonds. When double bonds occur, we know there is one sigma bond and one pi bond. One of your p orbitals is going to be occupied by the pi bond. It will not be able to hybridize. So since one of them will be occupied by the pi orbital, we only have 3 remaining orbitals left over that can hybridize and put us on the same level. So whenever we have something with a double bond, we end up forming sp2 hybridization, which means we can form 3 hybridized sigma bonds. Okay, we see this a lot with ethene. So this is C2H4. We know that one of the sigma bonds will hybridize, and then each of the H's will also occupy one of our sp2 orbitals. So if we were to think about it this way, this particular carbon is sp2 hybridized because it can form 3 bonds, and this particular carbon is sp2 hybridized because it can form 3 bonds. What happens is that the pi orbitals remain unhybridized, and when they get that overlap, it takes up one of our p orbitals. Okay. So here are a couple of other examples. We have BH3. We know that boron only likes to form 6, or only likes to have 6 valence electrons. So in order to form 3 bonds, it hybridizes to have sp2 orbitals. This is the same picture of ethene as we saw before, and it really shows nicely the step-by-step. First we have the sigma bond overlap, and then we get the pi orbital overlap. Okay. So then when triple bonds occur, like I said before, we know that we can form an additional pi bond due to the ability of pi orbitals to occupy 2 different planes in space. And so when triple bonds occur, we know we have 1 sigma bond and then 2 pi bonds. As a result of 2 of my pi orbitals being occupied by unhybridized pi bonds, we only have 2 orbitals left that can hybridize, and we get an sp orbital. If we think about the way electrons would spread out, then we would have 2 spaces available for 2 additional bonds to form. You'll see this most often when we're looking at something like HCN. We see that carbon has the ability to form only 2 sigma bonds, and then the 2 additional pi bonds are coming from this area here with the lack of hybridization due to the pi bonding. Okay. So the other example that was on there was acetylene. If we look at C2H2, we can see that we get overlap with these 2 sigma bonds that form here for this carbon, and same thing here. So each of these would be sp2, or sorry, sp, and then the pi bonds that overlap here and here are the result of those additional bonds. Okay. So one thing that's really important with hybridization is that lone pairs also have an effect on that hybridization. It explains why molecule geometries with lone pairs still fall under the same electron geometry because the energy levels are still the same. So for example, if we're looking at water, we know water has a bent shape, which means it has 2 sigma bonds and 2 lone pairs, but it still has a tetrahedral electron geometry because there are 4 total domains that have to form. So this is tetrahedral electron geometry, but a bent shape. All right. So lone pairs we know repel a little bit more, but if we have lone pairs on our center atom, they will take up 2 of your occupied orbitals, and you'd only have 2 remaining to form single bonds or sigma bonds. So if we look at something like water, it is still sp3 even though it only forms 2 bonds. Lone pairs count when you're looking at hybridization. If you're looking at something like NH3, we know NH3 is still a tetrahedral electron geometry as well, but we have that lone pair that counts. So it's still going to be sp3 hybridization, it's still going to be tetrahedral electron geometry, but it will have a trigonal pyramidal shape. Okay. When we're looking at this valence bond theory and hybridization, a couple of key things just to recap. We know that there's an orbital overlap between 2 atoms. We know in each orbital we can have a maximum of 2 electrons of opposite spin that can be present in overlapping orbitals. That makes sense, it lines up electron configurations. When we look at orbital overlap, the pair of electrons is found within a region to be influenced by both nuclei. Electrons are attracted to both atomic nuclei, and this leads to our bonding. So as the extent of overlap increases, the strength of the bond increases. So this also, like I said, helps explain why double bonds and triple bonds are stronger, because you have more overlap, right? If we've got a sigma bond or a single bond, we only have 2 orbitals overlapping. If you've got a double bond, you've got 2 s orbitals and 2 p orbitals overlapping. If you've got triple bonds, you've got a sigma, 2 sigma overlapping, and then 4 pi bonds overlapping, or 4 pi orbitals overlapping, rather. So because of that, it really helps explain why more energy is needed to break those bonds, because you're breaking more regions of overlap. Okay. So when we have maximum overlap, we form the strongest possible bond. Okay. One more thing to just kind of clarify, pi bonds will never form without a sigma bond first. I know I said that earlier, I just want to reiterate that point. All right. So then the last couple of hybridizations we really need to look at, and this should be relatively new, is DSP3 and D2SP3. If we are looking at things like phosphorus and sulfur, let's look at something like PCl5 and SF6. We know that those are really electronegative atoms, and they pull electron density away from phosphorus and sulfur. The reason we're able to form additional bonds, in addition to the lack of electron density, is the fact that phosphorus and sulfur can hybridize to form DSP3 orbitals, or DSP3 and D2SP3 orbitals. If we're to look at something like phosphorus, we know that we've got our p orbitals and then the d orbital, a little bit higher in energy there. What we can do is take one of those d orbitals and hybridize it with our sp3 and form a region that looks like this, where you have 5 different electrons that can spread out, and we get DSP3. If we needed 6, you could take a second d orbital and form 1, 2, 3, 4, 5, 6, and this would be D2SP3. Okay, and then this is why sulfur can have 6 possible bonding regions, because we can pair up this way. Okay. So some examples. Let's recap. If it's sp, you've got, I'll give you 2 examples. You got C2H2, which is carbon with a triple bond. We also have HCN. If it's sp2, we're looking at something that is trigonal planar. Trigonal planar molecules, you've got things like CO3 2-, you've got BH3. Tetrahedral, we can look at CH4, We can also look at water. It's important to know that things with lone pairs count there. Trigonal bipyramidal geometry, PCL5, and then look at SF6 for D2SP3 hybridization. It's key that each hybridization corresponds to a specific geometry. And when we're talking geometry, we're talking electron geometry here, right? Lone pairs still fall in there, so we could still have a tetrahedral electron geometry in the case of water, but be a bent shape, right? So just keep that in mind. We're talking electron geometry, the total number of domains. Essentially, the total number of domains or electron groups that you can have is equal to the number of hybrid orbitals, which then tells you which hybridization it is. So let's get some practice. Let's identify the hybridization of each of these carbons and then the one nitrogen. For A, what is the hybridization of this carbon? All right, well, it has 4 bonds, which means it's tetrahedral geometry, which means it should have sp3. All right, what about this carbon at B? Okay, the key here is that that double bond, that pi bond, does not count in your hybridization. You have 3 sigma bonds. That should be the way you determine this, how many sigma bonds. This would be sp2. All right, what about C? This carbon. All right, still 3 sigma bonds. This would also be sp2. And then this last one, nitrogen. Be careful with this one. All right. Remember, there's technically a lone pair here, even though they did not draw it. There's 3 sigma bonds and a lone pair. Remember, a lone pair counts towards your hybridization. This is still an sp3. Okay. We're going to see this a lot in organic when we're looking at organic structures. So you might see a problem that asks you to draw out the Lewis structure for something like this. I would draw them in order. So whenever you see a bunch of carbons in a row, it typically means they're in a chain. So I see something like this. I see another H. There's only one more thing bonded to that carbon. That O is going to have a double bond. And then we'll have something like this. Okay. Each carbon can only form 4 bonds. And actually, I think I just put an extra carbon in here, didn't I? Oops. Oops, oops, oops. Each carbon can only form the max of 4 bonds. If you're looking at double bonds obviously occupy part of that geometry. Okay. So using this shape, this structure, let's figure out the hybridization of each of these carbons. All right. So the one that's labeled number 1, what is the hybridization here? Should have said sp3. All right. What about carbon 2? Should have said sp2. There's a double bond. Now that pi bond does not count, so you have 3 sigma bonds. All right, carbon number 3. Okay, still sp2. And carbon 4, still sp2 because of that double bond. All right, so how many sigma bonds are in this molecule? So count up all of the lines in between. You ignore the double bonds here, the pi bonds. So the number of sigma, please determine your answer now. There are 10 sigma bonds here. How many pi bonds? There are 2 pi bonds here because there are 2 double bonds. Okay. Remember, there's a sigma bond between every single atom. The pi bonds are only there when there's a double bond. So the pi bond is referring to this, but the ones that are next to it are still sigma bonds. Okay, that is all for today.